Welcome back to Empowering Introductory Algebra, the informative series created to assist students to build a strong basic algebra foundation leading to those college-level studies. Hi, I'm Bob Young, Assistant Professor of Mathematics at Brevard Community College. With the help of the great support staff of WBCC, we continue to bring you introductory algebra lessons containing notes, graphics, tons of examples, and study tips. Let's pick up where we left off in our last lesson. Now, if you remember, we were working on application problems involving factoring using the quadratic equation. So let's go back to the graphic real quick and look at the 4 steps. So the first step is always when you're doing an application or word problem, know what the problem is asking. And number 2, assign a variable or variables to what is unknown. 3, translate the problem into an equation. And 4, solve the equation and answer what was being asked clearly. So let me scroll through a few graphics here. We did example 1 and example 2, which brings us to the next example 3, which states the product of 2 consecutive integers is 210. And they want you to find those integers. All right, so let's go to some examples here. And what are we after in this problem? Well, 2 consecutive integers. Now remember, that word consecutive means back to back. Remember, we did some problems earlier in the course with consecutive even and odd integers where they were 2 apart, but these just say consecutive. So we're going to go ahead and put for the first consecutive integer in algebra, since we don't know it, we'll call it x. And the next number, if the first one is x, if it's consecutive, would be x plus 1. So the problem stated the product of 2 consecutive integers. So the product, that key word meaning multiply, says go ahead and take the first integer x times that second consecutive integer, multiply them together, and that product would come out is equals 210. So again, we have some problems here where we're going to have to distribute the x through the parentheses, which will give us x times x is x squared. X times 1 is plus 1x, or just x, equals 210. So we can go ahead and solve now for x by doing what? Remember, yes, getting everything equal to 0. So we're going to have to bring the 210 over here by subtracting it from both sides. And we end up with the equation x squared plus x minus 210 equals 0. Now, some of you out there might go, my gracious, Young, look at these giant numbers in this problem. Now, don't panic. Remember those rules for factoring that we've been talking about for a long time now. The factors of the outside 2 will add to give you the middle. So 1 times 210 is 210. Now, factors of 210, that's going to add to give me 1 in the middle. Now, some of you are going, holy cow, Young, what's that? But if you think about it, 10 times 10 is 100. 20 times 20 is 400, so factors of 210 would have to be between 10 and 20 in order to add to give you 1. And it has to end in a 0, so for example, if I took the numbers 11 times 12, it wouldn't end in a 0. Or 12 times 13 would not end in a 0, it would end in a 6. So the first numbers I get to that would end in a 0 that are 1 apart would be 14 and 15. Now, do 14 times 15 multiply to give me 210? Well, let's come down here and we'll multiply it together real quick. And we will see that it is indeed the rainbow numbers, yes. So in order to add to give me a positive 1 in the middle, the signs would have to be a negative 14 and a positive 15. So when we factor this, and you know what they say, the bigger they are, the harder they fall, we get x plus 15 minus 14, or minus 14 plus 15, it doesn't matter. So this would be the factored form. So what makes this 0, what makes this 0 is my answers. Now you have to be kind of careful with a problem like this, and I'll tell you why here. So it looks like x would be negative 15, or x would be positive 14. All right. Now, some of you are looking at the answers, but wait a minute, Young. Are those consecutive integers, negative 15 and positive 14? No. No. See, so when you get these answers, remember, you have to clearly answer that question as the graphic showed earlier. Take each answer and plug it in back up here. So if x is 14 x plus 1 would be 15. So that would be one set of answers right there, 14 and 15. So those are consecutive integers. If you multiply them, you get 210. But there's another combination as well. If you plug negative 15 in here for x, x plus 1 would be negative 14. So that would be the second set of answers. So in this one, you have not one set of answers that make sense, but two. Now, is negative 15 and negative 14 consecutive integers? Yes. If I multiply them together, do I get positive 210? You betcha. So two sets of solutions for this application problem. So let's move on to the next graphic now, the next example. Example number 4, we'll do a few more of these application problems to give you a real good feel for them. States the base of a triangle is 4 centimeters greater than twice the height. The area is 35 square centimeters. Find the height and the base. So let's take a look at that one over here. And I've got a nice pretty picture drawn for you. Now, in the problem, it says the base of the triangle is 4 centimeters greater than twice the height. So in this case, they're comparing base and height. And I would let the height be x, since it would be the unknown. And then if the base is 4 centimeters greater than twice this, what would be twice x would be 2x, and 4 centimeters greater than that would be plus 4. All right, so again, just like when we had the rectangular problems earlier, they compared length and width. When they have triangular problems, they usually compare these two creatures, base and height. All right, and now to do this type of problem, we have to know this formula for area of a triangle, and that is 1/2 times base times height is the area of a triangle. So now the problem stated that the area was 35 equals 1/2 times base times height. Now, it doesn't matter which way I multiply these, and this is a concern here as well. I think I'm going to go ahead and put the height first, x, times the base after that, 2x plus 4. So the commutative property says it doesn't matter if I multiply base or height first. I think I like this format a little bit better. Now, what am I going to do here? I think I'll go ahead and multiply the 1/2 times the x and just call this 1/2 x and distribute that whole thing through the parentheses. What do you think? I think that'll work well. So 1/2 x times 2x would give us what? 1x squared. And there we have our good old friend x squared in the solution or the problem here. 1/2 x times 4 would be plus 1/2 of 4 is 2x equals 35. Look familiar? Why, certainly. All right, so now if we want to solve for x, we want to get everything equal to 0, keeping this number positive. So we'll take the 35 and move it to the right side of the equation. How? By subtracting it from both sides. So we're going to end up with x squared plus 2x minus 35 equals our hero 0. So now we can solve for x by factoring. And to factor this, factors of 35 here, to give me 2 in the middle. I think y'all are seeing these. If you've been working hard at it, you know, you feel that power surging in your veins. You know it would be 7 times 5 would be factors of 35, the outside 2 that add to give you the middle. Signs on the 7 and 5, for this to be a plus 2 would have to be a plus 7 minus 5. So those are your rainbow numbers, and you can sing a few bars, somewhere over the rainbows. Running out of paper here. I'm going to have to sneak this and factor it up here. So we would end up with xx to get the x squared, foiling in reverse, and then plus 7 minus 5 plus 7 doesn't matter. Okay, so it looks like my two answers for x are x equals negative 7 or positive 5, but let's remember now, this is a real world problem. I mean, can we put a negative 7 in for the height and plug it back in? Survey said, because we don't want that answer. That is called an extraneous solution. It makes no sense when we plug it in. But this second answer, 5, we can put in for x, and let's call it 5 what? Since the problem was given in centimeters, let's call it 5 centimeters. So the height would be 5, the base would be 2 times 5 plus 4. Let's go ahead and write that up here, show those steps, and that'll give you 14 centimeters for the answers. So height 5 centimeters, base 14. Read it back through in the problem. It will make sense. It will satisfy the equations. So we're doing great here. All right, next graphic. Now we're going to talk more about triangles, and this is an old Greek mathematician that came up with this one to torture students for thousands of years down the line, Pythagoras. Yes, so the Pythagorean theorem for right triangles, and this is where this is really used in real life a lot to measure distances and so forth. So the Pythagorean theorem, anytime you have a right triangle given sides A, B, and C, sides A and B, notice, contain the right angle. And side C is opposite the right angle, which is always the long side, and that's called the hypotenuse of the right triangle. And then sides A and B are called the legs of the right triangle. And what the Greek mathematician Pythagoras came up with was the formula that you see highlighted up there, a square plus b square, the sum of the squares of the two legs give you the long side, or the hypotenuse squared. And boy, what a revelation that was at the time. So they could measure all kinds of interesting distances there. And going on with that in mind, let's look at example number 5 here, our last application problem we're going to talk about. And then we'll move on to some more fun stuff. So number 5 is the length of one leg of a right triangle is 6 feet. The length of the hypotenuse is 2 feet longer than the other leg. Find the length of the hypotenuse and the other leg. Okay, so let's go ahead and look at the example on that with the right triangles here. So the problem stated the length of one leg of a right triangle is 6 feet. So we'll go ahead, it comes right out and tells us that one of the legs is 6 feet. So we'll write that information in. Now it doesn't matter which leg we call 6 feet. We'll just go ahead and, since this one's closest, call it 6 feet. And then it says the length of the hypotenuse is 2 feet longer than the other leg. So what's going to be x in this case is the second leg we're going to go ahead and call x, since it's being compared to the hypotenuse, which is going to be the long side, which is going to be 2 feet longer than that. So we'll call that hypotenuse x plus 2. So when you're doing these application or word problems, you have to read the problem carefully, make sure you identify what's being given, and get those variables lined up so we can solve and figure the rest of this problem out. So now the Pythagorean theorem says a squared plus b squared equals c squared. So you know what we're going to plug in for these, don't you? Right. We're going to take the 6 and we'll go ahead and call it a, and we'll call that 6 squared, plus b squared, we don't know what that is, so we'll just go ahead and substitute the value of x in there, and we'll call that x squared, equals c squared is going to be this x plus 2. Now here's where you have to be a little bit careful out there. This is going to be x plus 2 quantity squared. So we have our Pythagorean formula right here. And look what we have cropping up from the past here, a binomial square. So what do we have to do with that? Well, the 6 squared we know is 36 plus x squared. This we're going to have to take and multiply it not once, but twice. So whenever you see that, you know it's FOIL time. FOIL or be foiled. So when you FOIL x plus 2 times x plus 2, we're going to end up with x squared, first two terms. The outside 2 plus the inside 2 will give us plus 4x, plus 2 times 2, the last two terms will give us 4. All right, so now when we solve for x, some of you might say, Young, where do I take that x squared? Do I take it to the left or right? Well, in this case, it doesn't matter, because when I subtract the x squared to go either direction, what happens to it? The x squared goes out of the problem. So really, those can just cancel out. So whenever you have the same thing on opposite sides of equals, they just kind of go out for that reason. And then you're left with 4x plus 4 equals 36. And now to solve for x, let's go ahead and we got the variable on one side here. Let's bring the plus 4 over by subtracting 4 from both sides. And that gives us in the bottom here 4x equals what? 32. So to solve for x, divide both sides by 4, and we will get x equals 8. Now when you solve for x, again, don't jump for joy. Make sure you answer what the question is being asked. The 8 is what part of this right triangle? It is the second leg. That's what we let x equal. So we have to plug it back in up here, and it would be 8 what? 8 feet. And then the hypotenuse is 8 plus 2, which would be 10 feet. So we get a 6, 8, 10 right triangle. If you take that, square it, plus that, square it, you will get that and square it. So it does check here in the formula too. So the answer makes good sense. The hypotenuse is 2 more than that leg we didn't know, the unknown leg. So life is good. All right. So let me talk to you about the next topic here we're going to discuss. We are going to talk about, in the next sequence going down the line here, rational expressions. Rational expressions. Now, what does that word rational mean? If you think back from previous lessons, whenever you see the word rational in algebra, it means something to do with fractions. And I know some of you out there are like, oh no, not fractions again, Young, but yes, we can do these things, and we're actually going to do some with variables in them now, so it's even going to be more fun. All right, so looking at the next graphic here, I've got one on rational expressions. Rational or fractional expressions are quotients or ratios of polynomials. And I've got some examples here, real basic going to the more nasty ones. 2/3 can be written as 2 divided by 3. 7 over x minus 5, notice it can be written in that same format. Example 2, 7 divided by x minus 5. X plus 4 in example 3 divided by x squared minus 25. Notice we're separating the numerators and denominators with parentheses here. And make sure you do that so, you know, if you're going to write it in that second format there, that you can differentiate the top from the bottom on those. And the fourth one, a plus 5 divided by a squared minus 9a plus 8, can be written as that quantity divided by the bottom quantity. All right, so moving right along here, something about fractions we learned also. Because rational expressions indicate division, we must avoid 0 in any denominator. Division by 0 in mathematics is undefined. Remember why. We're going to get to that as well. All right. Now, what they're going to do first is they're going to give you some of these rational expressions with variables in them, and they're going to ask you to find all numbers for which each rational expression is undefined. So let's go to those examples next here, and we'll look at some. Find all numbers for which each rational expression is undefined. They'll give you the fraction, let's say 3 over 2x. Now remember, anything with a denominator of 0 in mathematics is considered undefined, and I'll go up here in the top and we'll illustrate that. 5 divided by 0. Now remember, if we wrote that the old-fashioned way, we did this in one of the previous lessons, we could take the bottom part, divide it into the top part of the fraction here, and what times 0 is ever going to give me a 5 under here? What times 0 is ever going to give me 5? There is no number. See, so that's why division by 0 is undefined, and you should try that on your calculators at home. Your calculators will really love that. If you say 5 divided by 0, you know it'll say, error, can't do it. There is no such number. See, so anything that comes out 0 in the bottom of a fraction is undefined, so what would make this fraction's denominator 0? 2 times what is 0? Now, if you want to, you can write that out, set it equal to 0. X, dividing both sides by 2, would be 0. So if I put 0 in for x here, that fraction would be undefined. All right, example 2, what makes this fraction undefined? Well, when y is what in the denominator? 7. So that's one you can kind of look at and see and tell. If I plug in 7 for y there, the denominator 0, undefined. Now remember, it's okay if the top comes out to be 0. So remember, we talked about that in lessons as well. Let's look at something with, if we had 0 over 5 in the top, we could divide bottom into top, 5 into 0, 5 goes into 0, 0 times, and we could check that by multiplying. So it's okay to have 0 in the top part of a fraction, but anything with 0 in the denominator, division by 0, undefined. Example 3. Oh, now Young, I can't just look at this one and tell what makes it 0 like I did on maybe these first two examples. So what are we going to have to do here? Well, we could factor that, knowing our rules for factoring, and get BB minus what? Factors of 4 that will add to give me 5, 1 and 4. So now, once I factor this denominator, I can tell what makes the bottom undefined or 0. Well, if b comes out to be 1, or if b comes out to be 4, this third example is undefined. And you know they're always going to mess with you on some of these. Like on example 4, look at this one. There's no number in the universe I can ever plug in for this x that will ever make this bottom 0, is it? So sometimes they'll say find all numbers for which it's undefined. In this case, they'll put none. There is no number I can plug in for x that will ever make that bottom 0. So Remember, division by 0 is undefined. All right, let's go to the next graphic here real quick. And we want to talk about rational expressions some more, so let's talk about multiplying them. To multiply rational expressions, multiply the numerators and multiply the denominators. All right, and equivalent expressions occur when multiplying both numerator and denominator by the same thing, which is really like multiplying something by 1. So let's go to some examples with both of those concepts. So I just picked some real easy examples starting out. Now notice there's no cross cancellation or no chopping here. I mean, if you try to chop this first example, you'll hurt your hand. You ever see one of those guys try to chop one of those concrete blocks and it wouldn't break, or they missed it wrong and their hand's going, ah! So don't try to cross cancel here. There is no common factors of 2 and 11 and 3 and 7, so we just multiply straight across and we get 2 times 7 is 14 over 33. All right, so numbers, not bad. Variables, same thing. 5x times a, we can write as 5x ax, or we could write 5xa using the commutative property, it doesn't matter, over yb or by yb. It does not matter. All right. Over here, same thing, variables. Now on the 3a, we would distribute that through. We could say 3a times x plus y all over b times z is bz. And, we could distribute it or we could leave it like that, but when there's nothing to cross cancel, that's how you just multiply fractions. And the next thing on that graphic, writing equivalent rational expressions. Like I bet you a lot of people out there in the studio audience could give me tons of fractions that equal 1/2. All right, let's think of a few. Some of you would say, well, gee, Young, that's easy. 2/4, 3/6, 4/8, 5/10, 100 200ths, and we could go on forever. Now, how are we getting these equivalent fractions to 1/2? Well, we're multiplying both top and bottom by what? The same thing. So to get 2/4 from 1/2, we multiply the top and bottom by 2. To get to 3/6, we multiply the top and bottom by 3. To get to 4/8, 4, 5/10, and so on. So we know that as numerical ways to make equivalent fractions. Does it work with variables? You betcha. Let's make some equivalent fractions to 2x over 3y, because we don't want those variables to scare you out there. So I'm going to go ahead and multiply this by c over c. I can do it with variables as well. The rule still works, and that would be an equivalent fraction of 2cx over 3cy. And I could do that with any variable, any quantity, or anything. Let me take another one here. I won't show it, but I'll take, how about 2x times 3x minus 5 over 3y times 3x minus 5. Would that be an equivalent fraction to what we started out with here? Why, certainly. Because we are multiplying by the same thing over itself, which is the same thing as multiplying by 1. And down here, third example, you can pick whatever you want, numbers, variables, anything, and multiply and get it. This one I'll go ahead and take and multiply by y over y. All right, so an equivalent fraction of a plus b all over c minus d would be y times a plus b over y times c minus d. And if we wanted to distribute that, we could as well. So we would have ay plus by in the top, multiplying the y through, divided by cy minus dy, my y slipped there, in the bottom. So equivalent fractions here, just multiply those same things by the top and bottom. All right, let's go to the next graphic. It's fun with fraction day. All right, rational expressions. To reduce rational expressions, remember anything divided by itself reduces to the number 1, or uno. Assume no denominator equals 0. All right, so let's look at some examples there. And most of you know these coming in. 8 over 8, Young. 8 divided by 8. Sure, that's 1. Anything divided by itself is 1. Works for variables. X over x. Now remember, x can't be 0 here because we can never have a 0 in the bottom. We talked about that. 1. X plus 4 over 4 plus x, does that commutative property bother you? Anything over itself, 1. Now remember, in this case, x could not be a negative 4, or we would have 0 in the bottom. That would be a problem. And even a large trinomial, look at this rascal here, 2x minus 5 plus x squared over minus 5 plus x squared plus 2x. As long as every single thing in the top and the bottom are identical, the fraction reduces to 1. And if you're not sure, you could always plug numbers in here for x as well. You could let x be 3, and you would get 3 plus 4 is 7 over 4 plus 3 is 7, and that would reduce to 1 as well. All right. Now, I know some of you are thinking, Young, where are you going with this? All right, let's look at the next graphic. To reduce rational expressions, anything divided by its opposite reduces to -1. And again, we're assuming those denominators are not equal to 0, so let's look at some examples of that. All right, so notice I slipped one negative over a positive, and remember, anything negative divided by positive gives you a reduces to -1. All right, even with variables, if you have opposite signs in the numerator and denominator, does not chop to 1, but it chops to -1. Now, a lot of people wonder about this one right here, a minus 5 over 5 minus a. They don't see that that reduces to -1, but look at the signs on the a. In the top, in the numerator, the sign is positive a, isn't it? Because I don't see no negative sign there. In the bottom, it's minus a. In the top, it's a minus 5. In the bottom, it's a plus 5. That also reduces to -1. These are considered opposites, very important. All right, now if you don't see that, plug numbers in for a again. So we can come over here on the side. You can put any number in there for a except 5, which makes it undefined, but we'll let a be 10, and we get 10 minus 5 would be 5 over 5 minus 10. Plugging that in would be -5, and you sure do see it reduces to -1. And yes, Young will challenge you with the viciousness here. Notice I take a trinomial, look at the signs on the 4x square in the top bottom, the 7x top bottom. Their opposites are all different. 2 top bottom, yes, even this creature will reduce to -1. Yeah. So reducing rational expressions is something we're really going to work on here a little bit, but it's just like reducing numerical fractions. Anything divided by its opposite reduces to -1. Now, notice I slipped you a Mickey over here. Now, let me go ahead and just isolate this guy right here. Well, Young, how about x plus 3 over x minus 3? Does that reduce to 1 or -1? Let's see. Are they the same? Well, obviously not. Are they totally opposite? No. So this one is considered a reduced rational expression. Do not try to reduce it. All right, so this is one that will not reduce. So if you put some numbers in there, you can check that. Let's put in 8 for x there. See, if I put in 8 for x on this one, if you're not sure if it reduces to 1 or -1, always be sure. We'll let x equal 8, and we end up with 8 plus 3, 11, over 8 minus 3, 5. So you notice that doesn't come out to be the same thing. It doesn't come out to be opposites, doesn't come out to be the same, so it does not reduce. All right, so what I want you to remember here now is anything over itself, 1. Anything over its opposite, -1. And if they're not the same and if they're not opposite, no chop, or you can hurt your hand. You can hurt your hand badly here, yeah. All right, so in closing, practice the algebra concepts presented to master each lesson. Keep your work organized with problems copied and steps shown in detail. Read related materials in your textbook. Work through similar examples and write down any key points to solidify your understanding. No one can do it for you, so take the initiative. It will pay dividends, I guarantee you. Take care. We'll see you next time.